GIS Fundamentals, Section 9, Basic Spatial Analysis. Spatial data analysis is the application of operations to coordinate and related attribute data. The terms spatial operations and spatial functions are often used interchangeably. Some practitioners insist an operation does not necessarily produce any output, while a function does. Spatial operations can be applied sequentially to solve a problem. A chain of spatial operations is often applied, with the output of each spatial operation serving as the input of the next. Scope. Spatial data operations may be characterized by their spatial scope, the extent or area of the input data that are used in determining the values at output locations. Local operations use only the data at one input location to determine the value at a corresponding output location. Neighborhood operations use data from both an input location plus nearby locations to determine the output value. Global operations use data values from the entire input layer to determine each output value. Selection and classification. Selection operations identifies features that meet one to several conditions or criteria. The simplest form of selection is an on-screen query. A data layer is displayed, and features are selected by a human operator. Selection splits the data into either the selected set or the unselected set. Set algebra. Selection conditions are often formalized using set algebra. Set algebra uses the operations less than, greater than, equal to, and not equal to. The set algebra operations greater than or less than may not be applied to nominal data, because there is no implied order in nominal data. All set algebra operations may be applied to ordinal data, and all are often applied to interval ratio data. Boolean algebra. Boolean algebra uses the conditions or, and not to select features. Boolean expressions are most often used to combine set algebra conditions and create compound spatial selections. Parentheses, brackets, or other delimiters should be used to specify the order of application. Spatial selection operations. Adjacency operations are used to identify features that touch other features. Features are typically considered to touch when they share a boundary. Adjacency is defined as sharing a boundary for some distance greater than 0. There are often several variations of any single spatial operation. Care must be taken to test the operation under controlled conditions until the specific implementation of a spatial operation is well understood. Containment is another spatial selection operation. Containment selection identifies all features that contain or surround a set of target features. Classification. Classification is a spatial data operation that is often used in conjunction with selection. A classification, also known as a reclassification or recoding, will categorize geographic objects based on a set of conditions. Classifications may add to or modify the attribute data for each geographic object. These modified attributes may in turn be used in further analysis. Classification may be used for many other purposes. One common end is to group objects for display or map production. A classification may be viewed as an assignment of features from an existing set of classes to a new set of classes. Classifications are often specified by a table or array. The table identifies the input class or values, as well as the output class for each of this set of input values. A binary classification is perhaps the simplest form of classification. A binary classification places objects into two classes, 0 and 1, true and false, A and B, or some other two-level classification. A potential drawback from automated class assignment stems from our inability to precisely specify class boundaries. Considerable time may be saved by automatic class assignment, but the analyst may have to manually change some class boundaries as the only way to achieve a desired classification. Equal interval classification simply subtracts the lowest value of the classification variable from the highest value and defines equal width boundaries to fit the desired number of classes into the range. Equal area classification class boundaries are defined to place an equal proportion of the study area into each of a specified number of classes. Another method for automated classification is a method based on natural breaks or gaps in the data. Natural breaks classification looks for obvious breaks. It attempts to identify naturally occurring clusters of data, not clusters based on the spatial relationships, but rather clusters based on an ordering variable. The modifiable areal unit problem. When there are no objectively recognizable categories, polygons may be reclassified and grouped in many ways. This general phenomenon, known as the modifiable areal unit problem, or MAUP, has been exploited by politicians in the United States and elsewhere to redraw political boundaries to one party or another's, but generally not the country's, advantage. The process of aggregating neighborhoods to create majority blocks for political advantage was named gerrymandering after Massachusetts Governor Elbridge Gerry when he crafted a political district shaped like a salamander. There are two primary characteristics of modifiable areal unit problem that may be manipulated to affect aggregate polygon values. The first is the zoning effect. The aggregate statistics may be changed by the shape of the units, and the second is the size effect, that aggregate statistics may change with the area of the units. The modifiable areal unit problem effects may substantially influence the values for each unit, and they affect many analyses based on the collected data. Dissolve. A dissolve function is primarily used to combine similar features within a data layer. Dissolve operations are usually applied based on a specific dissolve attribute associated with each feature. A value or set of values is identified that belongs in the same grouping. Each line that serves as a boundary between two polygon features is assessed. The values for the dissolve attribute are compared across the boundary line. If the values are the same, the boundary line is removed or dissolved away. If the values for the dissolve attribute differ across the boundary line is left intact. Dissolve operations are often needed prior to applying an area-based selection in spatial analysis. Proximity functions and buffering. Many important questions hinge on proximity, the distance between features of interest. Proximity functions modify existing features or create new features that depend in some way on distance. Distance values are calculated based on the Pythagorean formula. These values are typically calculated from a cell center to cell center when applied to a raster dataset. Buffers. Buffering is one of the most commonly used proximity functions. A buffer is a region that is less than or equal to a specified distance from one or more features. Buffers typically identify areas that are outside some given threshold distance compared to those inside some threshold distance. Raster buffers. Buffer operations on raster data entail calculating the distance from each source cell center to all other cell centers. Output cells are assigned an in value whenever the cell-to-cell distance is less than the specified buffer distance. Those cells that are further than the buffer distance are assigned an out value. Raster buffers combine a minimum distance function and a binary classification function. Vector buffers. Simple buffering, also known as fixed distance buffering, is the most common form of vector buffering. Simple buffering identifies areas that are a fixed distance or greater from a set of input features. Buffering on vector point data is based on the creation of circles around each point in a dataset. Buffered circles may overlap, and in simple buffering, the circle boundaries that occur in overlap areas are removed. Compound buffering. Compound buffers maintain all overlapping boundaries. All circles defined by the fixed radius buffer distance are generated. These circles are then intersected to form a planar graph. For each area, an attribute is created that records the number of features within the specified buffer distance. Nested or multi-ring buffering is another common buffering variant. we may require buffers at multiple distances. The formation of line buffers may be envisioned as a sequence of steps. First, circles are created that are centered around each node or vertex. Tangent lines are then generated. These lines are parallel to the input, feature lines, and tangent to the circles that are centered at each node or vertex. The tangent lines and circles are joined and interior circle segments dissolved. Variable distance buffers. The buffer distance may increase in steps. For example, we may have one buffer distance for a given set of features and a different buffer distance for the remaining features. We may wish to specify a larger buffer zone around large fuel storage facilities when compared to smaller fuel storage facilities. The variable buffer distance is often specified by an attribute in the input data layer. Overlay. Overlays involve combining spatial and attribute data from two or more spatial data layers. An overlay operation requires that data layers use a common coordinate system. Overlay may be viewed as the vertical stacking and merger of spatial data. Features in each data layer are set one on top of another, and the points, lines, or area feature boundaries are merged into a single data layer. The attribute data are also combined, so that the new data layer includes the information contained in each input data layer. Raster overlay. Raster overlay involves the cell-by-cell combination of two or more data layers. The cell values are combined in some manner and an output value assigned to a corresponding cell in an output layer. There are as many potential output categories as there are possible combinations of input layer values. The number of possible combinations is important because it may change the number of binary digits or bytes required to represent the output raster data layer. Raster overlay requires that the input raster systems be compatible. This typically means they should have the same cell dimension and coordinate system, including the same origin for X and Y coordinates. Data are normally converted to compatible raster layers before overlay. This is most often done using a resampling. Vector overlay. Overlay, when using a vector data model, involves combining the point, line, and polygon geometry and associated attribute data. This overlay creates new geometry. Overlay involves the merger of both the coordinate and attribute data from two vector layers into a new data layer. The coordinate merger may require the intersection and splitting of lines or areas and the creation of new features. Vector overlay functions typically identify line intersections during overlay. Intersecting lines are split and a node placed at the intersection point. Thus, topology must be recreated if it is needed in further processing. Any type of vector feature may be overlaid with any other type of vector feature. Overlay output typically takes the lowest dimension of the inputs. This means point in polygon overlay results in point output, and line in polygon overlay results in line output. This avoids problems when multiple lower dimension features intersect with higher dimension features. Clip, intersect, and union. Special cases of overlay. There are three common ways overlay operations are applied: as a clip, an intersection, or a union. The basic layer-on-layer combination is the same for all three. They differ in the geographic extent for which vector data are recorded and in how data from the attribute layers are combined. The intersection operation may be considered in some ways to be a spatial AND, while the union operation is related to a spatial OR. The clip operation may be considered a combination of an intersection and an elimination. A clip may be considered a cookie-cutter overlay. A bounding polygon layer is used to define the areas for which features will be output. This bounding polygon layer defines the clipping region. In most versions of the clip function, the attributes for the clipping layer are not included in the output data layer. An intersection may be defined as an overlay that combines data from both layers, but only for the area where both layers contain data. Features from both data layers are combined. Both layers serve as data and as bounding layers, so that any parts of the polygons that are in one layer but not another are clipped and discarded. A union is an overlay that includes all data from both the bounding and data layers. No geographic data are discarded in the union operation. Erase, or similarly named function, which is the complement to the clip function. In an erase function, areas covered by the input layer are cut out or erased from the bounding layer. A problem in vector overlay. Polygon overlays often suffer when there are common features that are represented in both input data layers. We define a common feature as a different representation of the same phenomenon. Two representations may differ even though they identify the same boundary on the Earth's surface. When the county and state data layers are overlaid, many small polygons are formed along the boundary. These sliver polygons cause problems because there is an entry in the attribute table for each polygon. Slivers are a burden because they take up space in the attribute table but are not of any interest or use. There are several methods to reduce the occurrence of these slivers. One identifies all common boundaries across different layers. The boundary with the highest coordinate accuracy is substituted into all other data layers, replacing the less accurate representations. Another method involves manually identifying and removing slivers. A third method for sliver reduction involves defining a snap distance during overlay. This forces nodes or lines to be coincident if they are within a specified proximity during overlay. Network analysis. A network may be defined as a set of connected features, often termed centers. Centers are connected to at least one and possibly many network links. Links interconnect and provide paths between centers. Network analysis, also known as network models, are used to represent and analyze the cost, time, delivery, and accumulation of resources along links and between the connected centers. Resources flow to and from the centers through the networks. In addition, resources may be generated or absorbed by the links themselves. The links that form the networks may have attributes that affect the flow. The concept of a transit cost is key to many network analysis problems. A transit cost reflects the price one pays to move a resource through a segment of the network. Transit costs are typically measured in time, distance, or monetary units. There are three types of problems that are commonly analyzed using networks: route selection, resource and territory allocation, and traffic modeling. Route selection involves identifying a best route based on a specified set of criteria. Route selection is often applied to find the least costly route that visits a number of centers. Selection of the best route involves an algorithm that recursively follows a least cost set of arcs beginning at the current node. A set of interconnected network links is identified, as well as start and destination centers. The route from start to destination locations is typically built iteratively. One route finding algorithm adds the least cost link at each step. Resource allocation problems involve the apportionment of a network to centers. Each center or arc is assigned to the nearest or least cost center. Variations on resource allocation include setting a center capacity. The center capacity sets an upper limit on resources that may be encompassed by a territory. Maximum distance also serves to limit the range of the territory from the center. Both of these restrictions may result in some unassigned areas, that is, portions of the network that are not allocated to a center. Traffic modeling is another oft-applied network analysis. Streets are represented by a network of interconnected arcs and nodes. Attributes associated with arcs define travel speed and direction. Attributes associated with nodes identify turns and the time or cost required for each turn. Illegal or impossible turns may be modeled by specifying an infinite cost. Traffic is placed in the network and movement modeled. Bottlenecks, transit times, and underused routes may be identified, and this information used to improve traffic management or build additional roads. Geocoding. Geocoding, also known as linear referencing, is another common application of spatial data networks. Geocoding is the process of spatially referencing point features based on the address of the feature and knowledge of an address range for the linear network. Geocoding requires a set of addresses associated with a set of linear features. Typically, at least the starting and ending addresses for links in a network are known. These starting and ending addresses define an address range, and the range is assumed to linearly span the connecting line. Points on the line may be geographically coded in that, given an address, we may calculate approximately where the address should occur on the network link. The estimated location of the geocoded address is based on a linear interpolation, beginning at the starting address and adding a length proportional to the address divided by the address range. Because geocoding only estimates address locations, these locations may contain substantial error. Geocoding typically involves a regular linear interpolation of an address across an address range. Address ranges are usually assigned ordinally, while the geocode is an interval estimate. This ordinal interval mismatch may be particularly bad in rural areas, where development over a long time period may result in substantial nonlinear address arrangements. These nonlinear addresses can cause substantial confusion, so any application of geocoded data must allow for these inconsistencies, or the data must be evaluated and corrected. GIS Fundamentals, Section 9. Basic Spatial Analysis, Section Summary. Spatial operations are applied to input data and generate output data. Inputs may be one to many layers of spatial data, as well as non-spatial data. Outputs may also number from one to many. Operations have a spatial scope, the area of the input data that contributes to output values. Scopes are commonly local, neighborhood, or global. Selection and classification are among the most often used spatial data operations. A selection identifies a subset of the features in a spatial database. The selection may be based on attribute data, spatial data, or some combination of the two. Selection may apply set or Boolean algebra and may combine these with analysis of adjacency, connectivity, or containment. Classifications may be assigned automatically, but the user should be careful in choosing the assignment. Equal area, equal interval, and natural breaks classifications are most often used. The resulting classifications may depend substantially on the frequency histogram of the input data layer, particularly when outliers are present. A dissolve operation is often used in spatial analysis. Dissolves are routinely applied after a classification as they remove redundant boundaries that may slow processing. Proximity functions and buffers are also commonly applied spatial data operations. These functions answer questions regarding distance and separation among features in the same or different data layers. Buffering may be applied to raster or vector data and may be simple, with a uniform buffer distance, or complex, with multiple nested buffers or variable buffer distances. Overlay involves the vertical combination of data from two or more layers. Both geometry, coordinates, and attributes are combined. Any combination of points, lines, and area features is possible, although overlays involving at least one layer of area features are most common. The results of an overlay usually take the lowest geometric dimension of the input layers. Overlay sometimes creates gaps and slivers. These occur most often when a common feature occurs in two or more layers. These gaps and slivers may be removed by several techniques. Network models may be temporarily dynamic or static, but they are constrained to model the flow of resources through a connected set of linear endpoint features. Traffic flow, oil and gas delivery, or electrical networks are examples of features analyzed and managed with network models. Route finding, allocation, and flow are commonly modeled in networks. Geocoding, or linear referencing, is used to calculate approximate locations along a linear segment when the endpoint addresses are known. Linear referencing may also be used to locate changes in linear feature characteristics, for example, road surface or accident locations.